So next we move on to the topic, that is yield point elongation. In the initial class, I have explained about the tension test. The mechanical properties like strength, ductility can be determined from the tension test. Apply uniaxial tensile load to a specimen, to a material, you stretch it. So the load is controlled. The load is given in increments by means of a load cell, and the extension or the elongation that takes place in the metal, it is read by means of an equipment, small device that is called strain gauge. So a plot of stress versus strain. Stress is calculated by load by the cross-sectional area of the specimen, and strain is the change in length, that is the extension divided by extension by the original length. So stress versus strain graph has been discussed. So you have seen that the stress versus strain, the curve increases to some point, that is strain hardening that takes place in the material, and then it drops down. That is the normal curve, general curve that is observed for most of the materials. For specific materials like low carbon steels, the curve is somewhat different. So what is the difference between this normal curve and for that one observed in low carbon steels? That we are going to discuss now. So that topic is known as yield point elongation. So yield point elongation, this is one of the important topic, yield point elongation. The normal stress strain curve that we have discussed in the initial class, stress versus strain, this is a normal curve. We have discussed the various portions of the stress strain curve: the proportional limit, elastic limit, yield point, beyond which the material deforms plastically. Then material undergoes strain hardening, increase in stress to cause further strain due to the previous plastic deformation. Then the ultimate load the material can withstand before fracture, and the onset of necking, that is localized plastic deformation that takes place at the point of maximum load, that is known as ultimate tensile strength, and then the load drops and finally results in failure, fracture of the specimen. Uniform elongation, total elongation, all this has been discussed very briefly. In detail, we will cover this topic under the heading of tension test. But for the discussion of yield point elongation, there are two types of curves. One is the normal stress strain curve, which undergoes strain hardening, and then beyond ultimate tensile strength, the curve drops, and finally the material undergoes failure. This is the normal one, which you have already known. The second type of curve, stress strain curve, which is normally found for the case of low carbon steels. Low carbon steels is this type of curve. The material is normal up to the point A, similar to the first figure. This is the figure 2. In the first figure and second figure, if you see, up to point A, both the materials are similar. Both the curves are similar. Stress strain curves are similar. At point A, this material undergoes, this low carbon steel, it undergoes yielding suddenly. Yielding, plastic deformation suddenly, and the stress drops. You can see that there is a drop in stress at point A. This point A, where the material undergoes initial yielding, is upper yield point, is known as upper yield point. And at upper yield point, the material undergoes yielding suddenly and the stress drops down to point B. This is the point B. This is known as lower yield point. This is known as lower yield point. At point B, the material undergoes yielding at constant stress. Under constant stress, the material undergoes elongation and then it continues to undergo strain hardening. That is, to cause further strain, you need to apply more stress, increase in stress to cause further strain, and again it reaches this ultimate tensile strength and the stress drops and it undergoes fracture. So up to the point A, it is similar to the figure 1, normal stress strain curve. And beyond this elongation, this is known as yield point elongation, where the material undergoes yielding at constant stress beyond point B, that is the lower yield point. Again, beyond this yield point elongation, the material follows the normal curve, undergoes strain hardening up to the maximum load, and then stress drops and undergoes fracture. But what is happening in this yield point elongation and why this is seen in this material, low carbon steel? What are the reasons for this? That will be discussed. So before that, I would like to discuss about some aspects of solid solution. You might have known about the types of solid solutions. That is a solvent atom, solute atom. Solute atom is substituted for the solvent atom if it is having somewhat nearly same size. Or it goes, the solute atoms goes into the interstitial sites if it is size is much smaller. Interstitial elements like carbon, boron, hydrogen, nitrogen, these go into the interstitial sites because of their very small size. So they form interstitial solid solutions. And whereas the atoms, the solute atoms, which have almost nearly the same size of the solvent atom, they form substitutional solid solutions. So whether substitutional solid solutions or interstitial solid solutions, both they strain the lattice, crystal lattice. These strains, that means they create strains in the lattice. These strains, they act as a barrier to the dislocation motion, thereby strengthening is due to these strains. So that strengthening is called solid solution strengthening. We will discuss the solid solution strengthening very elaborately in the next module or in the coming modules when I will deal about the strengthening mechanisms. So solid solution strengthening is one of the strengthening mechanism. But here, in order to explain why this yield point elongation occurs in this low carbon steel, and this specifically this occurs in some materials. So one main material or well-known example is the low carbon steel. Initially it is found in low carbon steel. So what are the reasons for this? I need to give you some introduction about solid solution hardening. So solid solution means solute atoms, they go into the sites of the solvent if it is having somewhat similar size, or they go into the interstitial sites if it is much smaller. Interstitial elements are carbon, boron, hydrogen and nitrogen. They occupy the interstitial sites. So whether interstitial or substitutional, they cause strengthening. The reason for this is because of the difference in sizes of the solute and the solvent that create lattice strains. These lattice strains, they react with the stress fields of the dislocations and thereby they cause strengthening of the materials. So this is solid solution strengthening. So now I'll draw a few figures of solid solution. If the solute atom is slightly larger, if the solute atom is slightly larger than the host atom, that is the solvent atom, in order to reduce the strains, these solute atoms, they migrate towards the dislocation course. In order to reduce the total energy, these solute atoms, they migrate to the dislocation course. If the solute atom, it is slightly larger than the solvent atom, then they occupy the positions below the edge dislocations. If the solute atom is slightly smaller, if it is slightly smaller than the solvent atom, then they occupy the positions above the edge dislocations. So this is the case for substitutional. If the substitutional solute atom is slightly larger, it occupies the position below the edge dislocation where the lattice is expanded. And if the solute atom is slightly smaller than the solvent atom, it occupies the position above the dislocation where the lattice is contracted. And for the case of interstitial solid solutions, or the case of interstitial solid solutions, where the solute atoms are very, very smaller than the solvent atoms, they occupy the positions below exactly below the edge dislocations, and they form atmospheres known as quadral atmosphere. So these atmospheres, they restrict, they act as a barrier to the dislocation motion. They pin down the dislocations. So these dislocations, they have to cross this atmospheres. So these are the obstacles for the dislocation motion. And moreover, these atmospheres, they are not seen at slightly higher temperatures, greater than about 400 degrees centigrade. Because of more thermal vibrations of the atoms, the solute atoms, they are torn away from these atmospheres. So this process, it ceases to operate at temperatures greater than 400 degrees centigrade. Now I'll draw the diagram for the case of substitutional solid solutions, where the solute atom, it is slightly bigger than the solvent, or it is slightly smaller than the solvent. So where it occupies, that was discussed. If it is slightly larger, it occupies in the locations below the edge. Slightly smaller, above the edge dislocation, where the lattice contracts, lattice expands. The larger solute atoms occupies the positions where the lattice expands. And the interstitial solute elements, that is the very, very smaller size when compared to the solvent atoms, they occupy below that means they form a row of atoms below the edge dislocations. So this atmosphere is known as quadral atmosphere. So this is the diagram for the case of substitutional solid solution, where the solute atom is slightly greater than solvent. Slightly greater. This is the solvent atom, and this is the solute atom, where it is slightly greater than this. So it occupies the positions below the edge dislocation where the lattice is expanded. Larger the size of solute atom when compared to the solvent atom, it creates lattice strains. The lattice gets expanded. If the size of the solute is smaller than the solvent, lattice contraction takes place. So this is the case of the substitutional solid solution, where the solute atom, it is larger in size, slightly larger in size when compared to solvent atom. solute atom. So this is the edge dislocation. Below the edge dislocation, they occupy the positions. Whereas for the case of solute atom, slightly smaller, solute atom, if it is slightly smaller than the solvent atom, then they occupy above the edge dislocation. I'm representing both in the same figure. So please try to understand that if the solute atom is slightly greater than the solvent atom, they occupy the positions below the edge dislocation. If the solute atom is slightly smaller than the solvent atom, they occupy the position above the edge dislocation. So two figures, I am combining it. I am not drawing a separate one for both the cases. Both the cases are superimposed in the same one. The third case which I am going to draw is in the case of interstitial solute atoms. In the case of interstitial solute atoms, which are very, very small when compared to the solvent atoms. This is for the case of substitutional. Solvent solute. This is solute atom which is slightly smaller, and this is larger solute atom. Interstitial solute atoms, they occupy the positions below the edge dislocation. So these are the interstitial solute atoms. So if you are able to understand these figures, it will be much more clear to you. Substitutional are two types. Substitutional, that means the solute atom is slightly larger than solvent or slightly smaller than solvent. So if it is slightly smaller, it results in contraction of the lattice. The solute atom is slightly larger than the solvent. It results in expansion of the lattice. So below the edge dislocation, where the lattice is expanded, larger solute atoms occupy the positions. Above the edge dislocation, where the lattice contraction takes place, lattice contracts, the smaller solute atoms occupy the positions. The next is, the second category is interstitial solute atoms, which are much smaller in size when compared to the solvent atoms. So these interstitial solute atoms, they occupy the position below the edge dislocation, where lattice expansion takes place, and they form atmospheres that is known as Cottrell, C-O-T-T-R-E-L-L, Cottrell atmospheres. So the dislocations, they are locked by these Cottrell atmospheres. These atmospheres are the barriers for the dislocation motion. And these atmospheres, they cease to operate. That means they do not operate beyond 400 degrees centigrade. The reason is, at such high temperatures, thermal vibrations are more intense. The mobility of atoms is more. So these operations or this effect do not exist above 400 degrees centigrade. So the reason for the formation of this yield point elongation in the low carbon steels is mainly due to the presence of interstitial elements like carbon and nitrogen. In the case of low carbon steels, the interstitial elements are carbon and nitrogen. The carbon and nitrogen interstitial elements, they form these Cottrell atmospheres. So the dislocations are locked by these atmospheres. And moreover, once the dislocations are torn away from these atmospheres, the plastic deformation continues. Again, if they are unlocked, again the dislocations are locked by these atmospheres. More stress is required to deform. Unlocking of the dislocations by these atmospheres gives rise to this lower yield point. That means this serrated region. This zigzag portion is known as serrated portion of stress strain curve. So this creates serrations in the stress strain curve. SERRATIONS. This is known as serrations. Locking, unlocking of the dislocations by these atmospheres that gives rise to the serrations in the stress strain curve. These are also known as structure strains. Structure strains. These are also known as structure strains and Luder bands. Luder bands. Here, for the case of normal materials, normal stress strain curve, where you have beyond the yield point, the curve increases because of strain hardening. The curve rises because of strain hardening, reaches to the ultimate load, and then the curve drops down. That is, the stress drops down. So there is a fall in the curve and material undergoes fracture. Whereas for the case of low carbon steel, up to the point A, the stress strain curve is similar to the normal curve. At point A, the material suddenly undergoes yielding. Dislocations move very easily. Stress drops. The point B is known as lower yield point, beyond which the serrations or structure strains, also known as Luder bands, are seen. Why? Because due to locking, unlocking of the dislocations by these interstitial elements like carbon and nitrogen, which forms the quaternary atmosphere. Once the dislocations are torn away completely by this quaternary atmospheres, the curve follows the normal stress strain curve. Strain hardening is seen up to the ultimate tensile load, and then the curve drops. The stress drops, there is a fall in the curve, and the material fracture. So at this point, the material follows the normal stress strain curve because the dislocations, they are completely torn away. That means they have completely crossed away the barriers. The barriers are the interstitial elements, carbon and nitrogen. They're completely torn away from these quaternary atmospheres. So normal strain hardening is seen, and finally the curve follows the normal curve. So the main reason for this yield point elongation, which is seen in low carbon steel, is due to the presence of interstitial elements like carbon and nitrogen, which forms quaternary atmosphere. So if you are able to understand the figures, that is for the case of substitutional, where atoms occupy the positions, solute atoms, and for the case of interstitial solute atoms, it occupies the positions below the edge dislocations and forms the atmosphere known as quaternary atmosphere. So there are certain disadvantages for the formation of this lower yield, the formation of this serrated portion of the curve are the structure strains, which are also known as Luder bands, that form during the plastic deformation of low carbon steel sheet materials. Okay, during the sheet forming operations, because of the presence of this yield point phenomena, it gives a very bad appearance on the surface of the sheet material during forming. The rough surface is seen, the Luder bands, the serrations are seen, which appears as very rough on the surface. So that gives rise to very poor surface finish for the steel, low carbon steel sheet materials. So during forming, because one portion of the material which has undergone plastic deformation, it gives rise to this yield point elongation, where the other portion has not yet received plastic deformation. So these structure strains or Luder bands are seen as rough appearance on the surface of the sheet materials during forming operations. So they form an objectional surface on the low carbon steel sheet materials during sheet forming operations for automobile parts. During deep drawing, so this is seen. This acts as a defect. So this appears as a defect. So in order to overcome this defect, in order to prevent this yield point elongation, a small cold rolling is given. A very small cold rolling is given before sheet forming, just before sheet forming, a small cold reduction of about 0.5 to 2% cold rolling is given. 0.5 to 2% cold rolling is given to these low carbon steel sheet materials in order to prevent this yield point elongation. Because of this small amount of cold reduction, 0.5 to 2% reduction, the dislocations, they are completely torn away by the atmospheres, and the stress strain curve follows the normal curve. So this yield point elongation can be eliminated by giving a very small amount of cold rolling, that is about 0.5 to 2% reduction. So this rolling is also known as temper rolling or skin pass rolling. The small amount of cold reduction, it is also known as temper rolling, or in other words, this is also known as skin pass rolling, because the main aim is not to reduce the thickness of the sheet. The main aim is to give a small cold reduction, thereby to avoid this yield point elongation, so that more number of dislocations are generated and they can easily move crossing these barriers, so that the dislocations can be easily torn away by the solute atoms and normal stress strain curve is observed, because they form an objectional surface during sheet forming processes. So for this yield point elongation to occur, the very small amount of carbon and nitrogen amounts are required, only very small amount. Carbon of about 0.002 weight% is required to cause this effect, and nitrogen also of about 0.001 weight% to about 0.002 weight% of nitrogen is required to cause this effect. Carbon of about 0.002 weight% is required. So in order to have this yield point effect, the amount of these interstitial elements, carbon and nitrogen, the required amount is minimum amount, very small amount is required. The amount is about 0.002 weight% carbon, and nitrogen, it is about 0.001 weight% to 0.002 weight% of nitrogen is required. So when these interstitial elements are completely eliminated, this effect is not seen. Even after giving this temper rolling or skin pass rolling, this effect will be seen if the material is left at room temperature for some time, because these elements, they again diffuse into the material and again form atmospheres. So as soon as this temper rolling or skin pass rolling is given, the material has to be formed. The sheet forming has to be carried out as immediately as possible after this temper rolling or skin pass rolling, to avoid this yield point elongation. Even after giving this temper rolling or skin pass rolling, if the material, it is left over for a few days, again if you form that material, reappearance of yield point elongation or yield point phenomena takes place. The reason is, with time, these carbon and nitrogen interstitial alloying elements, they again diffuse into the material and they form atmospheres. So this is known as strain aging. Strain aging means, if the material is left over after giving this temper rolling and skin pass rolling, if the material is not immediately formed, if it is left at room temperature for a few days, and if you try to form that material, the point at which the yield point has occurred is slightly increased, as well as the reappearance of this yield point phenomena is seen. That means the reappearance of yield point phenomena occurs at a slightly higher value of stress because of room temperature aging. So this is known as strain aging. The reappearance of yield point, at slightly higher stress at room temperature aging, due to this room temperature aging, is known as strain aging. So in order to clearly understand, I draw one more figure for this strain aging. I hope at least you have understood about the reasons for yield point elongation till now. The main reason for this yield point elongation, which is seen in low carbon steels, is mainly due to the interstitial solute at carbon and nitrogen, which forms atmospheres, quaternary atmospheres. So the dislocations, they are locked by these atmospheres. Thereby you have this yield point elongation, where the stress suddenly drops at point A, that is known as upper yield point. The material undergoes yielding suddenly at point A, stress drops. And at point B, the material undergoes yielding at constant stress, that is known as lower yield point. So once the dislocations are completely torn away from the atmospheres, then you can see the normal, this curve follows the normal path. So this region is known as yield point elongation. That is also known as serrations in the stress strain curve. It is also known as stretcher strains and Luder bands. The main reason for this is due to the interstitial solute atoms like carbon and nitrogen, which lock the dislocation. The dislocations continuously, they are pinned and unpinned, or they are locked and unlocked by the solute atoms. A minimum amount of carbon and nitrogen is required to cause this effect. So this forms an objectional surface for the low carbon steel sheet materials, mainly in sheet forming. This forms an objectional surface. It is similar to that defect, because it gives a very rough appearance on the surface due to this stretcher strains, also known as Luder bands. In order to eliminate this, a small amount of cold reduction is given by means of rolling, cold rolling. That is also known as temper rolling or skin pass rolling, because the main intention is not to deform that material. Main intention is to give slight amount of reduction of about 0.5 to 2%, so that more number of dislocations are formed and they can be easily torn away from the atmospheres, and thereby this yield point elongation will not appear. So this is the main reason for the yield point elongation, and in order to eliminate this, we give a small amount of reduction, that is known as temper rolling or skin pass rolling. But even after temper rolling or skin pass rolling, if the material is left at room temperature for a few days, again this reappearance of yield point phenomena is seen at slightly higher stress. Again, this reappearance of yield point phenomena is seen because of room temperature aging. This is known as strain aging. So this increases the strength of that material, but this defect, the stretcher strains, is not eliminated. Again, it reappears. So as soon as this temper rolling or skin pass rolling is given, these steel, low carbon steel sheet materials are to be formed as early as possible, because if time is given, sufficient time is given, carbon and nitrogen, again they diffuse and again they cause this yield point elongation. So this yield point elongation, that means the diffusion of this carbon and nitrogen as a function of time and a temperature, the appearance of this yield point, it depends upon the time and temperature, or it is a result of time and temperature, that is known as strain aging. So strain aging can be further explained by means of another curve. So this is the curve. Again, I redraw once. The material has loaded up to the point A. Suddenly, the material undergoes yielding. So this is known as upper yield point. This is known as upper yield point. Then the load drops suddenly to point B. So this is lower yield point. this is lower yield point. And at B, at constant stress, the material undergoes yielding. And again, the material, it follows the normal stress strain curve. It follows the normal stress strain curve. Because the dislocations are torn out from the quartal atmospheres. So if you load that material, if you load the material up to the point X, this is the point X, and unload that material, load the material up to the point X. That means you have crossed the yield point elongation and the material continues to strain harden normally. At this point, you have unload that material and again reload that material without giving sufficient time, without any time, immediately reload that material. So the material will normally follow the curve. So there is no appearance of yield point phenomena. Why? Because the dislocations have completely torn out from the atmospheres. So there are no atmospheres to lock the dislocations. So there are no serrations or there are no Luder bands, stretcher strains seen. When the material is loaded to the point X, unload that material, load this material up to this point, unload that material, and again reload the material immediately. So the curve normally follows the same path. Again unload that material. You have unloaded that material and give some sufficient time, for some days. Again you reload that material, give sufficient time, leave that material at room temperature for several days, and again reload that material. Upon reloading that material, you see the reappearance of yield point occurs at slightly higher value of stress. So initially the material has gone yielding at point A, but when you reload that material after several days, the reappearance of this yield point phenomena will occur at slightly higher stress. So this is known as strain aging. This increases the strength of the material. This hardens the material but decreases the ductility. This hardens the material. So this room temperature aging is known as strain aging. Hope you have understood this. Load the material up to the point A. You can see, load the material up to the point X. So point A is upper yield point where the material undergoes yielding suddenly. The stress drops and again the material undergoes yielding at constant value of stress. Stress is not changing. Stress is almost constant, but the material has undergone yielding to some extent. So this is known as yield point elongation. Point B is lower yield point. Then once the dislocations are completely torn out from the atmospheres, strain hardening is seen, strain hardening is observed. That means the curve follows the normal curve. So about point X, unload that material and again reload it immediately without giving sufficient time. Again load that material immediately. So you can see that there is no yield point elongation. So this region A, where yield point elongation is seen, and region B, there is no yield point elongation. Again unload that material. You leave it for several days at room temperature. So because of this room temperature aging, this yield point elongation again is seen. It reappears but at slightly higher stress than before, that is point Y. That is because sufficient time is given for the solute atoms carbon and nitrogen again to diffuse into the dislocation core and form atmospheres. Thereby again the reappearance of yield point is seen, yield point elongation, but at a greater stress than before. This is known as strain aging, that is static strain aging. Dynamic strain aging is the one which is seen at intermediate temperatures, that is around 100, 200, 300 degrees centigrade, at slightly elevated, slightly higher temperatures. During deformation itself, serrations occur in the stress strain curve. Very fine serrations occurs continuously in the stress strain curve. So that is known as dynamic strain aging. Strain aging that occurs during deformation is known as dynamic strain aging. It occurs at slightly higher temperatures. Because at slightly higher temperatures, these carbon and nitrogens, they interdiffuse. These solute atoms, they diffuse rapidly to form these atmospheres. Slightly higher temperatures, these solute atoms, they are more active and they rapidly form these atmospheres. So they form fine serrations in the stress strain curve. So this is for the case of static strain aging, and dynamic strain aging is strain aging that occurs during plastic deformation. Strain aging that occurs during plastic deformation. Strain aging that occurs during plastic deformation is dynamic strain aging at slightly higher temperatures, around 200, 300 degrees. But again, beyond 400 degrees, you don't find this. Why? Because at that higher temperatures, this effect will not exist. This formation of this quaternary atmosphere do not exist. So at higher temperatures, again, this effect is not seen. But this is static strain aging, that is the room temperature aging. Whereas this, if the aging occurs, the strain aging occurs at slightly higher temperatures, that is, and during deformation. And during deformation, if the strain aging occurs and at temperatures around 200, 300 degrees, it forms very fine serrations in the stress strain curve. The reason for this is the solute atoms, they diffuse rapidly to the dislocation course because of slightly higher temperatures. But beyond 400, this effect will cease to operate, because this effect will not exist, because there at higher temperatures the thermal vibration of the atoms is more intense. So this effect is not seen at greater than 400. This is slightly at higher temperatures, 200 and 300 degrees centigrade, and during plastic deformations the strain aging occurs, is known as dynamic strain aging. And this is static strain aging, where the material is loaded beyond the yield point, unloaded, again gives some time for the diffusion to take place, then again reload it. So the reappearance of yield point is seen at slightly higher stress. So this strengthens the material. And this is not beneficial for the case of sheet metal parts. Why? Because it gives a very bad appearance, a rough appearance. So this has to be eliminated. So to eliminate this yield point elongation, a small amount of cold reduction is given, that is cold rolling. That is also known as skin pass rolling or temper rolling. The percentage of deformation that is given is 0.5 to 2% deformation, mainly to eliminate this yield point elongation. But even though if you are giving this amount of deformation, immediately you have to form the part. Immediately you have to form the sheet metal part. Or else if you leave it for a few days, again this yield point phenomena is seen. So as soon as skin pass rolling is given, immediately form the part without giving enough time for carbon and nitrogen again to diffuse and form the quaternary atmospheres. So this is about yield point phenomena, strain aging, which is static, and dynamic, which occurs at slightly higher temperatures, that is around 200 degrees centigrade. But greater than 400 degrees centigrade, this effect is not seen, or this effect, it ceases to operate. The reason is, at such high temperatures, thermal vibrations are more intense. So this process or this effect is not seen at temperatures greater than 400 degrees centigrade. So briefly I have discussed about solid solution strengthening, which I am supposed to do it under the heading of strengthening mechanisms. But for you to understand what is quaternary atmospheres, So solid solution strengthening, slightly it has been discussed, so that you have a better understanding about what are these atmospheres, what is the reason for yield point elongation to take place. So by the end of this module, please, you have to do some assignment on the differences between the single crystals plastic deformation and the plastic deformation of polycrystalline materials. What is the main difference? Why fine grain are more stronger than coarser grains? What is equicohesive temperature? Why grain boundaries are higher energy? Then the yield point elongation. What is the main reason for yield point elongation? And it is seen in which material? That is the low carbon steel. What is the main reason for this yield point elongation to occur? Then what is strain aging? That is static strain aging and dynamic strain aging. What are the reasons for this? How do you eliminate this yield point elongation? And why you have to eliminate this yield point elongation? What does it cause on the sheet metal parts? Why you have to eliminate it? How can you eliminate it? And if you leave it, if you leave that material even after temper rolling or skin pass rolling, again it reappears at slightly higher stress. So immediately you have to form that part after giving this temper rolling or skin pass rolling. Now you have to answer all these questions by the end of this module, because this is what we have discussed about all these topics. So try to answer all these questions, because we have discussed all the main topics till now, and further we will be moving into the main properties, mechanical properties, hardness, tensile test, compression test, and different testing methods and different processes that take place at higher temperatures on the application of load, different types of failures, fracture, all this will be discussing. So this is the initial part of the mechanical metallurgy, the main small differences between single crystals, polycrystalline materials, etc. So once you are able to understand about all this, then you can put all these things into the forthcoming topics, so that you can have a much better understanding about the topics. So try to go through the reading material given to you, as well as carry out the assignment, so that in the forthcoming classes we'll move on to the other topics. So try to answer the questions which have raised in this at the end of this module.